Okay, so we're going to interpret predicted values, the slope, and the y-intercept of a least squares regression line. So we're going to start talking about those predicted values. So the predicted value y can be used to estimate the average outcome of a given value x. So for any given value x, the y hat is an estimate of the average value y, which we had already said. Y is going to be the real values, the real data. Y hat is always going to be an estimated value. So if we go back to when we were talking about the house sizes and the selling price, and we had this regression line, if we put in 3,000 square feet, what we see is that this is going to be the estimated price, or sorry, the estimated price of that house. So this is going to be a Y hat, is that if I have a house at 3,000 square feet, I estimate it's going to sell for $457.8 thousand. Now, the question is that really what's going to happen? Go back and find that data here. Thought I had it down a little bit. So scroll all the way to the top here. Oh, no, wait, I think that was my data set here. Yeah. And we look, it's like, that looks pretty maybe pretty reasonable because a house is just slightly bigger. That's what its cost is. So it seems pretty close. However, let's say we know that if X is going to be 2,735 feet, we know that Y is going to be 428. However, Y hat is going to being I'll have to go and calculate this here in a second. We're going to plug that in. Sorry, my square footage, not the price. But my Y hat, if I plug this into the formula, 1939 plus 0.002 times 2,000, times 2,735 square feet. There we go. We're getting this as a price. So this is what we're talking about estimated values and predicted values. I know that this house actually sold for this price, but if I were to make a guess and I didn't see the house or anything like that, all I knew is its square footage, I would guess that it sold for this amount, which isn't that far off. In actuality, this, like I said, this is a very close data set. I'm not going to have very many places where my values are going to be that far away. Like maybe here is like one of the houses and this one here, those are way off track from the actual costs. Like we look here, my Y hat is saying that if my house is about this size, my Y hat is saying it's selling for maybe let's say 478. When we see this actual value here, this Y is actually going to be 450, about 458. There's a $200,000 difference in the price than we predicted. So that's kind of a big price change. So I'm trying to grab my tool and go down. Okay, so like we said, we can use our equation to make predictions about Y. It doesn't mean they're always going to be what really happened, though. And then we were already talking about this a little bit. We want to interpret what Y would mean. So remember that our equation looks like this. That wasn't supposed to be a dot there. So let me go back and fix that. So this B naught is going to be your y-intercept. So this is a point where the line crosses your y-axis. So this was what was going on. This is my line. This point here is where my B naught would be. So it's that y part of it. So this has a practical interpretation only when the data contains both positive and negative values. So if your data contains both positive and negative values, like I have in this example here, so I have some negative x values, I have some positive y values, that 0 that's an interpolation point. It's inside of my data. So when I have both negative x's and y's, then the y-intercept is an estimated outcome for the value of the explanatory when the explanatory value is 0. Most of our data has not been looking like that. It's been actually this scenario here, where my data is like all out in here. So this is like my data was here and here. My data is only like just positive or only just negative. This point is still a point that I can find. It's just, does it have meaning? So in this case, 0 is an extrapolated point. So if the x value for all positive and all negative, if all your x values are all positive or they're just all negative, so they're not in between, then the y-intercept B naught does not have a useful interpretation. Unless 0 is in the data set, the point 0 B naught is an extrapolated point and is unreliable. So we can only really have any interpretation of y under this situation. Or not y, I'm sorry, B naught, your y-intercept. That's good. This is bad. This is not going to mean anything for us. So B naught is going to be the slope. Once again, y hat is B naught plus not B naught, B1 x. So B1 is going to be your slope. If the x value of 2 points on the line differ by 1, then their x values will differ by an amount equal to the slope. So this enables us to interpret the the slope YB, the slope B1. If the values of the explanatory variable for 2 individuals differ by 1, their predicted values will differ by B1. If the values of the explanatory variable differ by amount D, then their predicted value will differ by amount B1 times D. So 2 houses are up for sale. One house is 190 square feet and the other is, let's try this again, is 1,900 square feet and the other is 1,750 square feet. By how much we should predict their prices to differ? So this is when we're talking about that housing data, in which my B1 was 0.0992. Now, the size of these houses differ by 150 square feet. So the price increase my price increase from being at 1,750 square feet to 1,900 square feet is going to be that 150 square feet times that slope of 0.0992, which is going to come out to approximately $14.9 thousand. So if I increase the size of my house by 150 feet, I expect that the cost of the house is going to increase by almost $15,000. So that's how we can use our slope to make interpretations. Okay, so we want to get some meaning out of some of this here. So the data below is showing you that latitude of the center of the state and the mortality rate due to skin cancer. What is the meaning of the slope in the linear squares regression line? So we see that my slope is a negative 5.98. So what that means is that as x increases, so x is my latitude, as latitude increases by 1 degree, the mortality rate, because that's negative, the mortality rate is going to decrease by 5.98, so almost 6 deaths per million. So every time I go up 1 degree in latitude, out of 10 million people, we're going to have 6 less should be dying. So this does have an interpretation for us. That means that if I increase by 10 degrees, I go further north, a 10-degree increase is going to be linked to, not cause. It's going to be linked to a 59.8 decrease. To a decrease of 59.8 people deaths. Out of 10 million. And I'll be honest, I'm not sure if they mean these are deaths out of 10 million in the population or 10 million people who have skin cancer, but I think it's out of the population. What is the meaning of the y-intercept? Technically, your y-intercept is going to be 389.2. So in a way, it means we're at 0 degrees, so right in the equator. We expect that 300 and about 390 and 10 million. However, the problem is that 0 needs to be extrapolated. So that means that my y0, my y-intercept, so 0 degrees has to be extrapolated, so y0 has no reliable meaning. We don't really know what's going to happen at the equator. It's not in my data set. My data set ends here at about maybe, what did we say last time? Maybe like 26 degrees latitude. So I don't know what happens when I get closer to equator. Maybe like cancer rates significantly increase. Maybe they steady out. We don't know. And my very last question. Oh, so that was actually, it was for something else. Actually in Texas, just to point that out, the mortality rate is actually 161 out of 10 million. In Texas, actually, like on here, it said it should have been like 110. So like I said, it's not 100% in there. I think this is Texas, but I can't remember exactly. So that was a little artifact for something I was actually making and then I left.